Hello everyone, this is Professor Keen. In my last lecture, I introduced Newton's first and second laws of motion, and in this lecture what I'm going to do is talk a bit more about Newton's second law of motion. Okay, so remember last time, with Newton's second law of motion, I mentioned that there's really two components to this. First of all is that when you apply a force to an object, its quantity of motion or its momentum changes, and that quantity of motion change, the change in momentum, is proportional to the force impressed, or the applied force, and it's also in the direction of a line along the impressed force. So, Newton's second law, which is what we're talking about, it has two components: that the change in momentum is proportional to the applied force. That's point 1. And point 2 is that the change in momentum is in the direction of this force. Okay, so I want to expand on this a little bit. So, first of all, let's expand on this first part. This is a proportionality, and it's saying that if you know how much force is being applied, it doesn't actually tell you what the change in momentum is. It simply tells you if you double the force or triple the force, you're going to be doubling the change in momentum or tripling the change in momentum. There's a way we can write this as an equation, and I'm going to write that now. Delta P is equal to the force times the time interval during which this force is applied. So whereas the way Newton states it at first is simply in a proportionality, we can write this in terms of an equation, and we're basically saying that if you want to find out how much the momentum changes, you have to know the force that's being applied and also the time during which it's being applied. So for example, if you have the same force and you apply it for 1 second, it's going to cause a certain change in momentum. And if you apply it the same force for 2 seconds, it's going to have twice as big of a change in momentum. Or 3 times as long, delta t, you'd have 3 times the change in momentum. Okay? So really the force is proportional not only to the change in momentum is proportional not only to the force, but it's also proportional to the time interval during which this force is applied. So let's do an example problem. Before we go any further with the theory here, let's do an example problem. Okay, so let's suppose that I were to tell you that there's a surface. This is a very slippery surface, and on this surface is a block. The reason I'm using a slippery surface is so we can ignore drag, for instance. So let's just imagine there is no drag whatsoever exerted by this surface on this block. And let's suppose the mass of this block, let's use something simple like 1 kilogram. Okay? And let's suppose you hit this on the back and you apply a force in this direction. So there's a force being applied, and let's suppose that force is 5 newtons. We're going to use the International System of Units, even though that's not the system of units that Newton was using. Let's use that just to bring things up to date. Okay, so there's a 5 Newton force, and let's suppose this is applied for 2 seconds. So there's a constant force being applied for 2 seconds to the back of this. And here's my question. The question is, what is the final speed of this block, of this mass? Okay, so that's the question. How do we go about solving this problem? Oh, let me move this out of the way. Okay. So, as you might imagine, we're going to use Newton's second law. So we want to use the fact that the change in momentum that this block suffers, delta P, is going to be equal to the force we're applying to it times the time interval during which we're applying this force. Okay? So we know what the force is. It's a 5 Newton force. And we know the time interval during which we're applying it. It's 2 seconds. So we can right away find out the change in momentum to be 10 Newton seconds. Now this doesn't look like a change in momentum until we expand the units of newtons. So let's go up here and say the change in momentum is equal to 10. A little bit sloppy. The change in momentum is going to be equal to 10 Newton seconds. Somehow there's a lag time here. It's kind of frustrating to draw right now. See if there's something running that I want to get rid of. Okay, 10 Newton seconds. And what is a Newton? It's 10 kilograms meters per second squared times seconds, right? And so one of the seconds cancels out, and we have 10 kilograms meters per second, right? So you'll see that would give you a change in momentum, because momentum is a mass times a velocity. So let's write this out. The change in momentum, what do we mean by the change in momentum? We mean the final momentum, that's the momentum after you apply the force, minus the initial momentum, the momentum it had before you applied the force. We know that is 10 kilograms meters per second. And we know by the definition of momentum, the final momentum is just the mass of this object times the final velocity. And the initial momentum is its mass times its initial velocity. And that has to be 10 kilograms meters per second, right? Okay, well, we know the mass of this. We're told it's 1 kilogram. So I'm just going to divide every term here by a mass of 1 kilogram. So let's just divide every term by m, which we can do. So the final velocity minus the initial velocity is equal to these masses cancel out. And here we put a 1 kilogram mass down here, and so we're left with 10 meters per second is the final velocity minus initial velocity. So let's go back to our initial question. What is the final speed of this mass? We want to know what the final speed is, the final velocity. Now, can we determine the final speed of it? Well, technically we can't, because all we're doing from Newton's second law is determining the change in velocity. Remember, Newton's second law gives us the change in momentum. It doesn't give us a way of finding out what the momentum is. All it gives us is a way of finding out the change in momentum. And so we don't really know what the final velocity is unless we knew the initial velocity. So for example, if the initial velocity was 0, if it was originally sitting still, then we could say that the final velocity was 10 meters per second. It's sliding rightward after the application of this force with a speed of 10 meters per second. But if, on the other hand, the initial velocity, let's say, was 5 meters per second to the right, then because we know the change in velocity is 10 meters per second, now we'd say the final velocity is going to be 15 meters per second to the right. Or, to make things more interesting, if the initial velocity was, let's say, negative 10 meters per second, that is, if initially this block was sliding leftward with a speed of 10 meters per second, then what would the final velocity be after we apply this force? Well, the final velocity would be 0 meters per second, because it's originally going leftward at 10 meters per second. We're giving it a 10 meter per second or positive 10 meter per second change in speed, and so the final velocity is going to be 0. So it's important to keep in mind that Newton's second law, you need extra information to find out what its final momentum or its final velocity would be. Okay, so let me stop there, and that's a nice place to stop, because then it will give me a chance to see if I can fix this time lag on my sketchbook.